All right. Now that we've seen the diffusion signal, the apparent diffusion coefficient, the ADC, and how to reconstruct cue ball and constant solid angle diffusion ODFs, it's now time to look at spherical deconvolution. So what is spherical deconvolution, which leads to a fiber ODF, so a fiber orientation distribution function, or also called FOD, fiber orientation distribution, and the famous CSD model, which is often, very often, a default for tractography as a local model. So I'll go through a few slides and then show you a demo as usual in my Jupyter notebook. So as we saw in the previous slides, the diffusion ODF is quite limited around crossing fibers. So it's a good start, but it seems to almost only capture 90-degree crossings and is not that efficient at lower angles, where we clearly see other crossings there, but they seem to be missed by this Funk-Radon integral of great circles. And in a sense, as you'll see in these slides, it kind of makes sense because it's a diffusion ODF. And so if you have a tighter crossing fiber here with axons, we have to keep in mind that the diffusion ODF represents the likelihood of having diffusion along a certain direction. So if I'm a water molecule here navigating, well, turns out that if I ask my diffusion ODF, what is the probability there is diffusion along this intermediate direction? Well, it's still pretty high because of this, configuration. But if the question is, what is the probability of having a fiber along this intermediate direction? It's not the same question. It's a little subtlety, but it's basically 0% here, right? The likelihood of having a fiber. Here, the fibers are almost 100% in this direction and 100% this direction. And this is the difference between a diffusion ODF and a fiber ODF. And lots of book chapters and readings that you can look at to really get a clear notion and ideas about what this is. But so just to give you a brief idea, so we have a theoretical ground truth FODF, right? A perfect 100% two-directional fiber ODF. And what we in fact measure, if you actually go in the brain and you look at single fiber regions, right, where FA is super high, a FA of maybe 0.8 or 0.9, so you're in a very elongated single fiber population. Well, even if you measure the ODF there, what you find is that you have a certain width to it, a certain radial diffusivity. And so you can formulate this as, well, the true ground truth fiber ODF that we're looking for is actually built from the convolution between a potatoid and this ground truth ODF to give you a fat diffusion ODF from cue ball imaging, for example. And this can be seen either in the signal world with donuts and weird shapes, or in ODF world via the Funk-Radon Transform. So I think it's easier to imagine for first comers in the world of ODFs, but this can be seen in the world of signal. And so if we have a 60-degree diffusion ODF, 60 degrees, sorry, and we know the response function, so we kind of have an idea of what's this blurring. So this ODF, this fat ODF that I measure in the corpus callosum or in the internal capsule where we have a single fiber, right? So this is a single fiber model. Well, if I can estimate this guy, well, I can most likely deconvolve, so inverse the process to reconstruct a sharp fiber ODF. And in fact, this was developed in the mid 2000s by Donald Tournier, Flavio Dell'Acqua, myself. And so it helps in having smaller crossing angles. If you have also different volume fractions in the voxel, it helps. And now this is really the gold standard for fiber tractography because it's a sharper representation, and also as a result, it includes a model of white matter, because for us now white matter behaves like this cigar, and this is the object you want to give to tractography to better traverse crossing fibers and better represents white matter anatomy. So in the world of the signal, if you remember my diffusion signal in my demo, we can project it via the Funk-Radon Transform on the Diffusion ODF, and then deconvolve to get a sharper fiber ODFs. Or, as the original paper did, see this in the world of the diffusion signal. Now the response function is not a cigar, but the donut that we saw in my demo. And if we do deconvolve, we can reconstruct. If we're not careful, this is an extremely noisy process. So we tend to enhance high frequencies. And if we enhance fiber frequencies and we divide by things, we tend to accentuate noise. So if we don't do the constrained version, so that's hence the acronym CSD for constrained spherical convolution. If we do the unfiltered version, this is just a catastrophe. Everything here red is actually a negative number on the sphere. So this is not physical. And we see tons of green peaks that are just noise. But the constraint is just a nicer regularization process that nowadays is pretty well established. It enforces non-negativity, or it promotes it, and sparsity somehow, and you can really stabilize the numerical solution and get a sharp fiber ODF reconstruction, or FOD. And this Donald-Tournier, this was the first proposition. In 2004 was the non-constrained version, and in 2007 the constrained version. So pretty much at the same time as I was doing my PhD as well. So this is part of the Matrix package, but also now, of course, in DIPY as well. So in the world of the signal, it's the convolution between a perfect ground truth fiber ODF, a donut to produce the signal, and in the world of ODFs, like we saw before. So if you've been following what I have been saying, the key part here is this guy, the response function. How do we get this response function? Well, we have two options. Either we fix it because we have some a priori knowledge about the white matter, and this could be useful. Let's say you're doing mouse imaging or macaque imaging. The response function in a mouse or macaque is not going to be the same as in a human. But if you're doing human imaging, you might want to fix it yourself, or another option is to estimate it from the data. And so typically in the algorithms, we have automatic response function estimators. That's what we do in DIPY. And so a good solution is to go look for voxels where the FA is high, for instance, FA above 0.7. So we know we're in single fiber voxels, and this behaves like a diffusion tensor. So we can estimate this response function and then use it in the deconvolution process. So this is what is done when it's data driven. And if we have a population study, we can take the average of the population. So for instance, when I work on Alzheimer's disease or aging, well, it turns out that this response function is a little bit fatter than in healthy 25-year-olds. So this is something to consider and to think about. But once you have this object, you can actually deconvolve. So my recommendation to you is to either fix it with a good a priori knowledge, either as the average of your group, or just manually enter it and fix it in your solution based on literature. So this is possible, and of course you'll have control over these parameters when you use spherical deconvolution in DIPY. And so it turns out that this has a tremendous effect. Even if you have low number of direction here, like 45 directions, you see here the constant solid angle diffusion ODF, right? This is a diffusion ODF. That was the best we could do so far, but that we can see is still pretty potatoid looking in the crossing. Spherical deconvolution really has this sharpening procedure that allows us now to get all the potential crossing directions and that will help tractography. And so now we can do these beautiful reconstruction, you know, of the centrum semi-oval here, where you see a nice 2- and 3-way crossings between the corpus callosum here in red, crossing the cortical spinal tract in blue, the periodontal tract here, or the arcuate fasciculus here in green. And as a bonus, we can also start getting maps or metrics from the ODF reconstruction, fiber ODF. So just to remind you that as opposed to a T1 where everything is white in the white matter, even though you have, you know, contrast in FA, multiple crossing fibers, the T1 information is just white. One has to be careful that now with crossing fibers, it's important to capture maybe anisotropy, but along specific directions. Okay, so this now has a new term called the fixal, right? We want a fixal-based anisotropy. So orientation anisotropy, there's no convergence on names yet, but you could very well, you know, imagine a population study where your controls have this diffusion tensor, and suddenly your patients with degenerative disease have a more elongated tensor. So this is actually an FA going up. Well, in fact, what's happening maybe is just this green direction is deteriorating, and the blue and red direction in the ODF are fine. So this is really, really tricky. This may lead to an increased FA where actually only one fixal, this fixal, has anisotropy going down. So suddenly we can investigate a little deeper into going beyond DTI measures, and this has been coined either apparent fiber density or hindered modulated orientational anisotropy. So a lot of now the term AFD has seemed to win a little bit in the literature in terms of names. So the apparent density, and the idea here is just the more green cylinders you have here, the higher the surface area in B here. And the higher the surface area, the bigger your donut in the fusion world. And the bigger your donut, the bigger your Funk-Radon integral in a sense. So the stronger, the more elongated this peak of fiber ODF, this fixal. And this you can actually play with my simulator. And so if you play around with the signal here, you can see that the amplitude of this peak is a proxy to basically the fixal or the orientation anisotropy. So you can extract that from the code. So nowadays we have this new sexy name for fiber element, the fixal. And so you can start following anisotropy now per peak, right? So now I show you 3 pixels, pixel 1, 2, and 3 here, where they all have the same FA, kind of FA of 0.4, but you can see now the apparent fiber density for peak 1 versus peak 2 at each voxel, and this is different. So you can really truly follow the apparent fiber density here of the arcuate fasciculus along the fixals of the arcuate fasciculus. So we're starting to get, you know, options for now crossing fiber robust anisotropy measures. So this is of course very novel and still work in progress to be integrated with tractometry, but if you start getting and playing with Python, you can do all these things. And so we can create these voxel average maps. So what is the max apparent fiber density, or what is the total apparent fiber density, the average of everything going on in the voxel? Or another one here is NUFO, which kind of summarizes, you know, is it 0, 1, 2, or 3 crossing fibers within each voxel? So, you know, dark gray here is 1, light gray is 2, and very light gray is 3, for instance. So now I'm going to show you a demo where again we use our same 1, 2, 3 fiber simulations. I show you the response function, the CSD model, and how to extract apparent fiber density and NUFO. So, where's my Jupyter notebook? So we're now still in the same Jupyter notebook of part 1, but now I get into the small bit of code of constrained spherical deconvolution. I'm going to create or declare the constrained spherical deconvolution model from the reconstruction modules of CSD. I'm going to here in this example fix a response function. So you can see this is a response function with a diffusion tensor of 1544, exactly like in my slides. So almost 4 times more elongated than wide. So the radial diffusivity here is 4, and the length of the principal eigenvalue is 15. And then I'm going to give this response function to the constrained spherical deconvolution model for spherical harmonics order 8 by default, create the model, fit the model, and extract the fiber ODFs. You can see now, and if you rerun this demo, as opposed to the cue ball model, which was a diffusion ODF, and now here, after this constant solid angle model, which was a diffusion ODF, but properly normalized, now you have the spherical deconvolution, which really has this strong sharpening. So you can go back to the signal, generate 2 or 3, 60 degree, 45 degrees, and enjoy that. And the last thing I'm showing you is also how to extract the number of peaks. So the NUFO, in this case, is 2. And the total apparent fiber density in the voxel. So it turns out mathematically, if you look at the papers, this is just the spherical harmonics coefficients of order 0, because a bit like the Fourier transform, the average on the sphere is encoded in the first 0 order coefficient. And this is it for now. You can reconstruct nice spherical deconvolutions, fiber ODFs for a whole brain, and then watch the other demos to do fiber tracking.